So let's say that you look through your telescope and you see a satellite orbiting a planet way off in the distance, and you want to know what is the mass of that planet. So what we're going to do today is talk about how we get that mass. So since the satellite is orbiting the planet, we know that the satellite is accelerating because it's changing its direction. And we're going to use Newton's second law to guide us through with this. So we're going to start with the sum of the forces equal mass times acceleration. And we know that it's the gravitational force, big G m1 m2 over r squared, that's making the satellite accelerate. When you accelerate in a circle, that's v squared over r. What we can do is we can cancel out the mass of the satellite because that's the orbiting object with this v squared over r. And we can cancel out one of these radius. And by doing algebra, we can divide both sides by g so that those g's go away, and multiply both sides by r so we get those r's to go away. And we get the mass of the planet equals v squared times r over big G. And things are good. We just now need to know what r, v squared, and g are. So through your telescope, maybe you look at this and you measure the distance that the satellite is away from the center of the planet. That's going to be r. And let's say that you find that that r is 5 million meters. We know big G, that's a gravitational constant, that's 6.67 times 10 to the minus 11. And it needs v then, that's what we want to know. Well, by just looking at this satellite as it orbits around, as it orbits around, we don't know the v, there's not a speedometer on it we can see. So we have to look at the time that it takes to go around. So in this simulation, we see the satellite going around, and it takes about 3 seconds to make one rotation around the planet. Well, that rotation, though, is not actually real life. We're actually looking at a sped up version. So it's taking 3 seconds, but it's actually 3,000 times what real life is. So that means that this time would be 9,000 seconds to do that. So now to get v, remember v is distance over time, which is 2 pi r over our time, which is 2 times pi times our radius, or the distance between the planets, which is 5 million meters, divided by our 9,000 seconds. So we can do the calculation, and we get 3,489 meters per second. And we can use that value in here for our v squared. So we get the mass equals 3,489 squared times our radius, which is again our 5 million meters, divided by big G, which is 6.67 times 10 to the minus 11. And we calculate all that in here, and we get 2.6 times 10 to the 20th kilograms. So that's how you get the mass of a planet.